Okay, so yesterday we did the theoretical values, and you should have gotten a line, very linear, of one. And the day before that, we got a line as well, although it's hard to see because my scaling is so big, because I used a lot higher heights in the simulation than I was able to do in my living room. So it's hard to see, but you can see that there is a really flat line here. Notice that the lines do not have the same slope. They do not. Um, but they both are very convincing lines. 0.9992 and 1 correlation values are very, very good. So they are lines. This one has a very small intercept compared to how big its highest energy is, whereas this one is this one has a fairly noticeable um, y-intercept in the negative, suggesting that maybe there's some kind of error there. So, with that being said, um, let's talk about what a Newton or what a joule is. Well, if I come here and I look at this guy right here, we know that a joule is the same thing as a Newton meter. And we also know that a Newton meter is the same thing as a kilogram times meters per second squared. One quick note is that if you were to use an elastic energy equation, you're probably going to get something like this. Whereas if you're going to use the kinetic energy equation, you're going to get this, but they all lead to the same thing. They're all a joule. So knowing that, if I know that a joule is that, then let me increase this. I know that the slope of this is a joule over a meter. Well, a joule, the question is which one of these is more useful to use? Well, let's just try the Newton meter. So I'm going to put Newton meter in for joule because that's what a joule is, divided by meters. Wait a minute. If you do joules times meters over meters, the meters will cancel, leaving you with newtons. So now the question is, what has units of newtons?